Hello, everyone. Welcome to my presentation on the Fourier series of a sawtooth waveform for our course on signals, spectra, and systems. My name is Eric Seletaria, and today we will be diving into the mathematical decomposition and simulation of this unique signal.
To begin, what exactly is a sawtooth wave? It is a non-sinusoidal periodic signal defined by its distinctive shape, a linear ramp followed by an almost instantaneous flyback to its starting level. This waveform is a powerhouse in engineering, widely used in everything from electronic timing circuits to digital audio synthesis for music production.
When we look at a centered sawtooth for Fourier analysis, three properties are vital. First is periodicity. It repeats identically every period. Second is odd symmetry, which mathematically means the function at negative time is the negative of the function at positive time. Finally, because of this odd symmetry, the resulting Fourier series is composed entirely of sine A components, with no DC offset and no cosine terms. Mathematically, we can represent this signal in three different ways depending on our needs: the trigonometric form, the exponential form using complex numbers, and the combined trigonometric form, which helps us visualize magnitude and phase.
Starting with the trigonometric form, we focus on calculating the specific coefficients that determine the weight of each harmonic. These coefficients are what allow us to rebuild the sharp saw shape using only smooth sine waves. We begin with the trigonometric form, where we mathematically decompose the sawtooth into its component sine waves. In the file, you'll see our base parameters defined with amplitude A and period t. Because our waveform is centered and has odd symmetry, the coefficients a 0 and a n are 0, leaving us only with the sine coefficients, bn. The first graph displayed is the reconstruction plot. Notice how the signal begins as a simple sine wave, but as we increase the number of harmonics, the sum converges toward the sharp saw shape. You can observe the Gibbs phenomenon, those small ripples at the transition points, which is a classic signature of reconstructing discontinuous signals. The exponential form provides a more elegant and compact representation. By using Euler's formula, we can represent the series using complex exponentials, which simplifies many advanced system calculations. To dive in, we can proceed to our MathCAD file.
Moving to the exponential form, we represent the signal using complex exponentials and the coefficient c sub n. This form is vital for visualizing the line spectrum of the signal. If you look at the magnitude spectrum graph, you can see the energy of the signal distributed across both positive and negative frequencies. The amplitude of these spikes decreases at a rate of $1 per n, showing that higher-order harmonics contribute less and less to the overall power. This provides a much cleaner mathematical view for filtering and system analysis.
We also have the combined trigonometric form. This representation is particularly useful for engineers as it combines the sine and cosine terms into a single periodic function with a specific phase shift. To dive in, we can proceed to our MathCAD file.
The combined trigonometric form, or magnitude phase form, is where the math meets real-world engineering. Instead of separate sine and cosine terms, we use a single cosine wave for each harmonic with a magnitude c sub n and a phase shift theta sub n. The graphs here highlight the phase spectrum, showing how each harmonic is precisely timed to lag, or lead the fundamental frequency. By adjusting these phase values, we can see exactly how the timing of different frequencies builds the steepness of the linear ramp. This is the most practical form for analyzing how hardware circuits introduce delay.
Theory is only as good as its verification. I utilized MATLAB to simulate the Fourier series. This allowed me to visualize how the waveform converges into a sawtooth as we sum more and more harmonic components. To dive in, we can proceed to our MATLAB file.
Continuing with our MATLAB simulation, we begin with initialization to define the fundamental parameters, amplitude, period, and the number of harmonics, n. We then transition to signal generation, where the code implements the Fourier summation to digitally reconstruct the waveform. Through the visualization section, we plot the reconstructed wave against the ideal reference to visually confirm the convergence of the series. Finally, in the error analysis section, we identify the Gibbs phenomenon, observing the characteristic ringing that occurs at the signal's sharp transitions. In the plot we made, we clearly simulated an ideal sawtooth wave within the command windows of MATLAB.
Taking it a step further, I use Simulink to create a block-level simulation. This visual approach helps us understand how a system generates these signals in a more functional, hardware-like environment. To dive in, we can proceed to our MATLAB Simulink file.
We transition to the Simulink simulation, where we move from static math to dynamic block diagram modeling. We compare three distinct methods for generating the Sawtooth waveform. Manual construction. This method uses individual sine wave blocks and a sum block to physically reconstruct the signal harmonic by harmonic. It is the best approach for visualizing how adding specific frequencies slowly builds the linear ramp, though it becomes cumbersome as the number of harmonics increases. Programming. Method. Using the MATLAB function block, we implement the Fourier series algorithmically. This approach is highly flexible and efficient, allowing us to change the number of harmonics, n, instantly via code without adding more physical blocks to the model. Built-in method. For high-performance simulations, we utilize native Simulink blocks like the repeating sequence or signal generator. These are optimized for simulation speed and provide a mathematically perfect sawtooth without the harmonic ripples seen in the Fourier approximations. Comparing these, the manual method is ideal for education. Programming offers the greatest control over the spectrum, and the built-in blocks provide the most stable reference for system testing. To dive in, we may proceed to read more.
Before moving to hardware, I conducted a full circuit simulation. This step ensures that the electronic components we've selected will interact correctly to produce the precise ramp and flyback characteristics we analyzed earlier. Let's jump in with the simulated circuit in LTS-PICE.
Simulation phase, we examine the LT-SPICE circuit simulation, which bridges the gap between mathematical theory and physical hardware. The circuit utilizes a constant current source to charge a capacitor, ensuring the voltage rises in a perfectly linear ramp rather than a standard exponential curve. Once the threshold is reached, a rapid switching mechanism triggers an instantaneous discharge, creating the characteristic flyback effect. This stage is essential for identifying real-world constraints, such as switching delays and component tolerances, that our ideal Fourier equations cannot predict.
Here you can see the results from my actual circuit experimentation. This oscilloscope capture confirms our theory and simulations, showing the real-world performance of the sawtooth generator. For those interested in the deeper mathematics or detailed simulation plots, I have included additional materials here that expand on our core findings. To explore them, let's look into our MathCAD file.
Finally, we examine signal transformation, where we apply mathematical operations to manipulate the waveform's physical characteristics. In the MathCAD file, you can see how amplitude scaling is used to stretch the ramp vertically by multiplying the function by a constant factor, a. We also explore time shifting, which moves the sawtooth horizontally across the time grid by adding or subtracting a delay value, TO, within the function's argument. Furthermore, we observe time folding, or reflection, where we reverse the time axis to flip the direction of the linear ramp. These transformations are vital for synchronizing signals in real-world systems, such as matching a scanning beam's position to a master clock in a radar or display system.
That concludes my presentation on the Sawtooth Waveform and its Fourier series. Thank you for your time and attention. I'm now happy to answer any questions you may have. Please like my video and subscribe. It will help me create more like this. Have a great day.